let's start with the presentation.
Good morning, everyone. Now we are going to tackle the complex, very interesting problem of the vortex canal. So, if we hit a box, we can obtain a vortex ring that propagates like that. So, the presentation will see some definitions. How does the vortex rings move? How does it stop? And the final parameters. First, what is its range? How do we define the range of the vortex? So, we define the range of the vortex by using a thin sheet of paper. And if the sheet is moving, that means that the vortex has reached it. And then we move the paper sheet backwards. And if the paper sheet doesn't move, that means that we have the vortex wings hasn't reached it. And we define the range like this. So we have a vortex ring that propagates, and if the vortex ring stops just before the paper sheet, we have the range of the vortex, and of course we take into account the uncertainties. Now, second definition. What is a vortex ring? It is a moving torus with a vorticity, like that we have on the photograph. So, we have a torus with a radius section A, a big radius R. There is a vorticity omega within the torus here. So we have speed little u, so the fluid is swirling around a torus section, so the fluid is swirling like that, and it induces a velocity v, and the vortex propagates. And so we have the circulation gamma around a torus section here with the definition. The first question is, how does it move forward? So, if we have this model, in the literature we can find an expression of the velocity for such a model, which is this expression. So, what can we see on this expression? So, it depends on the circulation gamma. That is to say that the vortex ring moves forward thanks to the circulation gamma. That is to say, thanks to the fluid that is swirling around a torus section and which induces a translational velocity v. We can also notice that it depends on the big radius r of the torus and the little radius l. So, this expression comes from the literature, and what is really interesting and what I would like to present to you now is that we can find an order of magnitude of this velocity thanks to a little calculation by using an analogy with electromagnetism and the Biot and Savart relation. So, here is the analogy. So, the analogy is between magnetic field and the speed. And here is the expression of the calculation. So, if we have this scheme, by considering little radius A very little compared with the big radius R, we can make the calculation and then we find this result. When we compare it to the exact result, we can see that it is the same order of magnitude, so we can easily and with a simple calculation find it again. Now, the second question that comes is, what does the ring stop? So, there can be 3 main points, which are the diffusion, the friction with the air, and the stability of the vortex. So, first of all, the diffusion. So, the diffusion comes from the fluid that diffuse, and so that the rings can disappear. So theoretically, we have this expression of the little radius A that can increase in function of the time. But experimentally, we have plotted the little radius A in function of the time. So it is in blue, and if we compare to the theoretical point, we can see that experimental data are consistent with the theory and that radius A is indeed slightly increasing, but in such scale of time we can consider it as constant. Now, the friction with the air. So the friction with the air comes from the viscosity, which is not equal to 0. So on this video, we measure in function of the time the velocity v, the radius of the torus, the little radius of the torus section, so as to deduce the circulation gamma in function of the time. So here is the definition. What are the results? Here is the result of the velocity v in function of the time with the arrow bar. And we can see that the velocity v is decreasing almost linearly during the time. Then, if we have a close look on the big radius r, we can see that the big radius r is increasing during the time, and if we take two photographs at the beginning, we can see that we have this radius, and at the end, we have this radius. So, as we can predict, as the experimental data shows, we can see that the big radius r is increasing. And here, if we have a close look again to this expression, we can see that if the big radius is increasing, it makes the velocity decreasing. Last but not least, now I plot the circulation gamma in function of the time, and we can see that the circulation gamma is decreasing during the time. So what can we conclude from that? The circulation gamma is decreasing because of the viscosity. That is to say that U, that is to say the fluid that is swirling around the torus section, is decreasing because of the friction with the air. And at the end of its trajectory, we have the fluid which is not moving anymore, so the circulation equals to 0, and thanks to this expression, we can see that the velocity equals to 0. And we can see that on this video, with the vortex cannon, big radius r is increasing, the fluid is swirling, but the swirl is decreasing, and now the fluid is not moving anymore. Gamma, the circulation is 0, and the velocity is 0. The vortex ring is stopped. Now, the stability. We define the lifetime of the vortex ring as the time before disappearance or stop. And we can believe that this lifetime depends on the perturbation on the vortex ring. That is to say that if I have a box, that is to say a vortex cannon, and we apply a force on it, like this, if we apply a big force on it, we'll get big perturbations on the vortex, and we can believe that the lifetime will decrease in function of the force that we give to the box. So, if the force is increasing, the velocity is increasing, that is to say, the Reynolds number is increasing, so it makes more turbulence, and we have the lifetime that is decreasing. How to verify it experimentally? We use this experiment, we have the vortex cannon, and we leave a mass fall on the cannon, so as to communicate an energy to the cannon. And we measure the range of the ring, and thanks to a little reasoning that I can explain after, if we have the time, we can see that the lifetime of the vortex is decreasing quite slightly in function of the height, that is to say, in function of the energy given, or as I said, in function of the force. So, if the force is increasing, we have the lifetime that is decreasing. So, now we better understand why the vortex stops. The final range. We have answered the question, why does it move forward, or how does it move forward, and why does it stop? Now we can answer which parameters related to our cannon can we tune. The parameters we have observed and we have studied is the size of the container, the diameter of the circular opening, and the force applied. Let's now see how does the range of the ring vary in function of these parameters. First, the size of the container. We took 3 boxes with different dimensions, a little one, a medium one, and a bigger one, and we measure an order of magnitude for each boxes. And we find different order of magnitude, so we can conclude that so as to get a bigger range, we need a bigger boxes. With an observation, bigger boxes need a bigger impulsion so as to create a vortex ring. Now, let's see the diameter of the opening. We use a little vortex cannon and we make the little diameter vary, and we plot the range in function of this diameter, or in function of the ratio of the areas. And we have a maximum here around 30 degrees. So the range is maximum for the relation between areas of 30 degrees. Finally, we compare the range with the force applied, or I say the force, but we better say the energy. And thanks to this experiment that is the same as before, we can plot it, and we can conclude that the range is increasing with the energy applied, but we didn't get a maximum. And another observation is that the velocity is also increasing with the energy applied. So we have to apply the best energy as we can, and that does not break the box, so as to get the better work.
The time is up, please make conclusions.
So it's concluded. Important factors are the circulation gamma, both radius, the turbulence, and the parameters on which we can tune is the size of the container, the diameter, and the energy applied. And we made the final experiment with those parameters, with those dimensions, the ratio of the area, and the highest force that did not break the box, and we obtained this range of the range. Thank you.
Now it's time for the questions of the opponent to the reporter.
You go to slide 16. So, on which side did you apply the force on the box?
On the upper side.
Okay. And you mentioned that you increased the box size, but was the relative size of the hole the same?
The ratio of the areas was the same.
Okay. And can you go to slide 12? Yeah. Okay. Thank you.
Okay, so now is the time for preparation of the opponent. Can we start?
Okay. Yes. So my name is Anders, and I'm the opponent from the Danish team. First, the good part about your presentation. First of all, it was really nice. You had really nice videos, I think, to show the phenomenon, so we clearly understand what's going on here. You had a really good physical explanation of the phenomenon, so we also clearly understand how you see this phenomenon. You had references, first of all, and your comparison to the Biot-Savart law was very, very good, I think, and was a good way of calculating the velocity yourself and compared to literature. So I think that's really, really good. On the other hand, I would like to know how did you measure the radius of the outer shell? You did mention how you measured it, and from the videos you showed, I think it's quite hard to see the actual radius, and especially how it changes. So I would like to hear how you actually did that. And you mentioned how you could measure or calculate the circulation. but also you didn't state how you could measure it actually, because I think that's pretty difficult, and that could be really interesting to hear. You also said at some point that you could clearly see that the velocity was decreasing as time went by, but I think that it was quite hard from your figure to actually see that the velocity was decreasing, because you have quite large error bars, and it wasn't such a big decrease in velocity. Would like to hear a comment on that. And you mentioned a lot of important parameters, which was good, but I think you missed one, and that is the time the force is applied to the box. How long interval do you apply the box? Because I think that's really important, and that can maybe have something to do with, are the vortex ring actually stable for all times here? And lastly, you said that the vortex ring become unstable when the circulation is zero, because there the velocity is zero. However, do you think that the vortex ring actually becomes unstable before we have zero circulation?
Should we move to the discussion?
No, I had some more general discussion. As I said, do you think the vortex ring becomes unstable before circulation is zero? And also you mentioned that what decreases the velocity radically is diffusion and friction. However, which term do you think dominates this loss of velocity?
So we move to the discussion between the reporter and the opponent.
Yes, sure.
So, thank you for your comments. To answer your question in the right order, so concerning the measure of the little radius A, what I did is that I used this video and I pointed each image, I pointed each parameter, that is to say the little radius, the big radius, and the velocity. Concerning the little radius, I measured it thanks to software called ImageJ, and I measured it here. So I admit it is not very precise, but I put the error bars in consequence, and we can also have this explanation with the theoretical explanation. If the initial radius is 4 millimeters, after 0.3 cm, we have 4.5 millimeters. What we can also say is that anyway, I think it is an answer to this question. Concerning the circulation, as I said, I measured the velocity, both radius, and thanks to the formula, the relation of the velocity, I can deduce the circulation in function of the time.
Okay, thank you. I would like to hear you comment on first of all, how did you apply the force to the box?
Okay.
Which method did you use?
Concerning the speed that is decreasing, it is because of the friction with the air, and it is decreasing linearly, and at the end we can expect that it is, if we have this, it is decreasing more like this to reach zero. Concerning your question right now, the force, I applied it on the upper side. Why? Because it was a mean to get a constant force, because I used the energy. I use the energy, so if I release a mass on the bottom, on the box, the energy I use is the mass per the weight and the height. So
So you make sure that the energy you're applying was constant in all experiments.
Yeah, and during my experiences, when I want to make the energy vary, I use different heights. So, for example, if my box is here, I will use the mass here, then here, and I can know the energy I apply to the box So I can be quantitative and precise.
Okay, but then if we now say that you can change the energy you apply with a certain height, however, if you can also say that we have the same energy applied, but we can change the time at which we apply it, how do you think that will influence the results?
That's a good question. What I think is that when you apply a force, there are two important parameters. That is to say, the fluid, the mass of fluid, the quantity of fluid you make move, and the initial speed. That is to say that if you have a box like this, and you release a mass on it like this, you will make the box, this mass of fluid vary. For example, if we have a motion of the box like this, and you'll get an initial speed like this. And if we do this little and simple physical reasoning, we have this energy applied, and which is transmitted to the box with this expression. We get the impulse, the time impulse, and we can get the initial speed here with this expression. So the two important parameters is the displacement here and the velocity, the initial velocity here.
Okay, so one last question. How do you think the radius of the hole in the box, or how do you think the stability of the vortex ring depends on the hole radius?
It depends. Like this?
I mean, can you have a certain
Please answer the question.
Yeah, because if we have no wedges, the box is closed, so we don't have a vortex. And if the whole wedges is open like this point, you have a vortex, but it doesn't propagate. So you have a maximum here, and that's the optimal parameters for the wedges.
Okay, thank you. Now it's time for the questions from the reviewer.
Thank you for the discussion. I have a question to the opponent. Out of the mechanisms of the ring destruction, which is the most important?
You mean when it becomes unstable?
Yes. What is the most important mechanism? There are outline mechanisms.
I think it's the loss of circulation. That's most important.
And the reporter, please. What's your opinion?
Sorry?
Main factor why the ring is destroyed.
The loss of circulation too, as I explained, and the perturbation that increases.
Okay, may you explain more clearly, the reporter, which method of measuring of distance? So you have a sheet of paper, which is moving right near the ring during whole experiment, yes?
Yeah, imagine the box is my laptop. I hold the sheet of paper, I hit the box. If my sheet of paper is moving, I go backward. I do it again. If my sheet of paper is still moving, I go backward. It is not moving, I go forward, and I do like that.
So sheet of paper is moving between the bucket, yes?
Between them?
Between the bucket, between the creation, one motion of the sheet of paper, yes?
Yeah, I do it several times to determine precisely the range.
Okay. One question about the thickness of the ring. Yeah. Actually, which is changes of this magnitude during the whole motion of ring. Now during the north 0.3 seconds. You have 25 meters of distance. And what's the size of the ring in the beginning and at the very end? Thickness.
The thickness is here, so you have 4 millimeters.
Quarter of second, but I'm interested of the changes of this magnitude during whole moving of the ring.
You have the changes of magnitude in function of the time.
So the ring is moving quarter of second, 25
so
meters.
it is increasing, but you have a little scale of time compared with the range. So the increasing is not it's light, and we can consider it as constant.
Okay, time is over. Preparation of the reviewer's speech.
Good morning, everybody. My name is Roman Bedroy, and I'm a representative team of Ukraine. And I'm going to present my review speech on the problem number 2, Vortex scanning. Well, first, we thank both the reporter and the opponent for the presentation and the fruitful discussion. And now we'll move on, breaking down some of the points. And we'll start with the advantages of the report. We think that you presented the function setup, which was really useful, and you started with an elegant and short demonstration of the phenomena right on the first slide that gave us an understanding of what we're going into. You introduced your model where you talked about what is a vortex and how long it lives and so on. That gave us an understanding of a framework in which you're going to work. Then we saw a theoretical description where you outlined 3 factors that might influence the vortex as it's going through, and then you focused in detail on every single one of them: the viscosity, the diffusion, and the stability. We really enjoyed your BSL analogy, and we think that was an elegant way of having a research and theoretical part. Then you had an experimental check where you showed for every single point of those 3 destruction tools, you checked the diffusion, viscosity, and stability points by having separate experiments. That was really good. And you also talked about optimization of geometry, size and diameter of the vortex scan, and then you talked about the force that was applied. You used references, and you had very nice pictures. That was remarkable. At the same time, we think that there were some disadvantages of the report. First, we think that the choice of the vortex depth criteria is quite unclear. You just had a piece of paper, and we have some concerns about that we hope to raise during the general discussion. For example, that the ring, how is your ring different from a simple airflow? Because the paper analogy cannot really detect that. Airflow slows down prior to the collision with some objects. That might be also a problem. We also have some optimization concerns because you maximize the velocity but not the range. And when you maximize the velocity, the stability might decrease, which is a big concern that we hope to raise both with the opponent and the reporter. Opponent noticed a lot about the experimental methodics, and you cleared out a lot of things about the experiment. At the same time, reporter did not put into the time, and opponent noticed a lot about the way the applied force was measured. We really think that was important. Opponent also mentioned, as I said, about the force, and made general methods of experiments clear. That was extremely important. At the same time, opponent has some disadvantages. We think that there was no general analysis of the solution, and the opponent's speech was rather short, and with rather a list of questions rather than the speech itself. We hope to outline a lot of those things that we mentioned during the general discussion, and I hope that it will be rather fruitful. And I have some discussion points outlined here, so I hope that we can start it now. Thank you for your attention.
If I can add something concerning the measure of the range, as I said at the beginning of my presentation, I defined the range of the ring with my definition with the paper sheet. I think and I believe that is the more precise way, is one of the most precise way to determine it. So I define it like that. I carry out my experiment like that. It's a choice, and I think this choice is quite good.
I have a question for the reporter, first of all. Do you, if you have a certain box dimension, do you believe that you can get a stable vortex ring for any radii of the whole point? For any radius of the whole? I mean, if you have the side of the box, do you believe that for a very, very small hole, for instance, you can get a stable vortex ring?
The stability depends more on the energy that you apply, yes, it depends more on the energy. So if you have a little radius, you can have a stable vortex. The thing is that if you have a little radius, you have to hit the box not too much strong, so as to get a stable vortex. Because if you hit the box too strongly, you'll get a high Reynolds number, and you'll get more turbulence, more perturbation, and you will lose instability of your vortex.
Okay, so the force applied is a factor that influences. Could you please list other factors that are influencing the process? And opponent, I want to hear your opinion on which factors should the reporter also consider in his research that he did not consider, that influence the range?
Concerning the factors, there is the energy applied, so the force, and as the opponent mentioned it involves 2 main factors, that is the initial velocity and the motion of your box. Then there is the ratio of the areas, that is to say the radius of the box, as I said, and the size of the box. That is the main factors I mentioned, and we can play on.
Okay.
I believe,
Any other parameters?
I believe that the material of the box is very important as well, and also the way you apply the force is pretty important because that determines how large a volume you can actually excite in.
That's a good remark because what is important is the motion of the box. So if you hit it like this or like this, you'll get the same motion, but maybe you'll get, excuse me for latency.
Yes.
You'll get a better speed if you hit the box like this because the speed will be like this. Because if you hit the box from the upper side, the speed will be like this and then like this. But if you want to actually, the reason why I choose the upper side, it is for the experiment. I release the mass with an initial height, and it is a precise way to get quantitative data and to make conclusions on my experiment.
Yeah. Also, here you filled the box with smoke before the experiment, right?
Yeah.
In which way do you think the smoke influences this experiment? Can you make it with just air, for instance?
To me, the smoke is just a way to see the vortex. And it is the reason why I use the sheet of paper to define the range. Because if you've got a vortex ring with smoke, and then the smoke disappears, it doesn't mean that the vortex ring has disappeared. So I mean that you can have the smoke that disappears, and then the vortex continue going like this, and the range stops here. So the smoke is just a funny way and a sexy way to see the vortex.
So the smoke is just an indicator. That we got that point. Another important question regarding the stability. You're maximizing the range by the velocity, but when you're raising the velocity, you also increase the chance of the ring to be unstable.
That's it.
And
I would like to mention that any team member can join our discussion now.
yes, but let me just finish the point here.
Yeah, I see your point.
The instability increases, and so is that the optimal way of optimization, just raising the velocity and opponent? Do you have ideas in that as well?
I got a quantitative answer for that. And it's a good question because if you raise the energy, you increase the initial speed, but you make the lifetime decrease. But we can, thanks to this little reasoning that I show, the initial speed varies, that is to say, the initial speed varies with the square root of the height, that is to say the square root of the energy, and I plotted the lifetime in function of the energy, and we have a graph like this. But if we get the slope here, we've got 0.2 and 0.5. That is to say that if you apply a greater energy, you'll get more greater speed than the lifetime will decrease, so you will maximize the range of the ring.
Okay, question from the Denmark.
I'd like to ask a question to the slide where you had this square root of h things and stuff like that. You say, if I remember the slide correctly, you say it's decreasing, but as I remember seeing it, that's one of the initial data points, which is actually just as low as some of the things in the end. So do you think it's oscillating, or is it really just decreasing? No, it's not that one. One with the slides.
With that?
Slide, sorry, I don't remember the exact number.
Tell me.
Just go back a little bit. Yeah, I think that this one.
Yeah.
Oh, so yeah. So you say it's decreasing, but the way I see it, some of the initial points are just as low as the final points, and it's really all within the uncertainties. So do you think you can really draw any conclusions from this slide?
It is a good remark, and I think it is at the core of the problem, because at the core of the stability. And you all know here that the stability, the turbulence, and the perturbation is a very complex problem. What I quantified here is that, as you said, the lifetime is decreasing, but it is decreasing more slightly than the initial speed is increasing, and at the end, you've got a better range.
Okay,
Question from the Ukraine.
You haven't asked a question about experimental statics. Can you please go back to the slide with a demonstration of the vortex ring?
This?
Yeah, please. So, with a video.
Sorry?
Video.
When you start the
So-
playing.
I've got a question to Zoltan. How do you think the ring which is going up and then goes down. How does it influence results of the experiment?
Going up and down? Sorry.
I believe that the vertical motion is due to loss in circulation, because the more circulation is lost, the more unstable the vortex ring becomes, and then you have this stochastic movement up and down. So I believe it's due to instability.
And also probably the temperature that we're looking for might be there because the smoke might be high. But it depends on the methodology.
I think that's neglected. If I should just comment on the question we had to me before about the stability, as the reporter mentioned, it's very important about the energy you apply. That's very important. But I'm not sure it's that easy. I think it's a combination of the energy you apply, the relative size of the hole of the box, and the box material. And so I think there's a certain region where those three parameters have to be optimized to get a stable vortex ring.
And also, talking stability, the last point that I have, the way I understand stability is that there's a ring, the vortex, and this radius A that you have, it varies. There must be oscillations on the surface, and they definitely impact the way it destructs. Yeah. So there definitely should be a correlation between the velocity and this A function of time, the way it oscillates. So again, could you clear it out? By increasing the velocity, what happens to it?
I think we understand it same way. There are 2 points. I showed before that we can consider this radius as approximately constant during the motion of the vortex. Then, if we raise the energy, we raise the instability, the perturbation, and it will be more unstable, and your vortex will move like the way you described it. So, I think I've already answered to the question, because you've got the right time and the square root of the energy, and at the end, to answer the final question.
Time's up. Now we can go to the concluding remarks by reporter. The discussion is over.
Sorry. I think this was a very complex problem, and this was really interesting. One of the things that is very hard to answer is the stability, but I believe that I managed to get quantitative data on it. We had a discussion on the way to optimize it with the opponent and reporter. I believe that we understand the problem and the different issues the same way, and we have managed to get a better understanding of the problem and a better optimization so as to maximize the range in function of the parameters I have mentioned before.
Now it's time for questions from the jury.
Yes, I have questions for the reporter. When you conduct your optimization, you have used some graphics from parameter of the boxes, for example, volume, radius of hole, and force on the box. And you use dependencies from one distance from one value for fixed two other parameters. It's well in case when real dependencies of distance from these three parameters is simple multiple of functions from only radius times functions from only value and times from function from only radius of hole. But
excuse me, what is the question?
The question is, did you check that this dependence from boxes parameters is simple multiplication?
To answer the question, the final optimization of the range, I used a box with these parameters. It was a cardboard box I think we are obliged to fix parameters at the beginning, that is the box. Then I use the best ratio of the area, and I use the highest force that did not break the box. Afterward, of course, the box, the material of the box have an influence, and if I had more time, I would have been pleased to study the shape of the box, the material of the box, but I didn't have enough time, and I used this final experiments to optimize the range.
So I have a question about the way you just produce these vortices. Your way is unsymmetric with respect to the movement. Don't you are afraid that it might destroy the stability of the vortex?
I used two experiments. This one, when I hit the box on the upper side, that's why you are mentioning. Why I did that, as I said, it's a way to quantify the energy given.
This I understood, but...
Yeah. And then the second experiment is this one, and as you said, I hit the box on the side, so because, as you said, it is better. But I am obliged to make choices, and to quantify the energy, I was obliged to use this experiment.
As I have a question to the reporter. You have a formula which is your theory, right? And it contains three parameters: the gamma, the A, and the large R. And your radius. Yes? And what you do is you try to measure independently the small radius, A, the big radius. Yes, and now I wonder, and then you measure the velocity, right? And from that you deduce your gamma.
That's it?
Yes. So what if the theory instead had been proportional to gamma squared? Would it have changed your optimization result in any way?
If it has been proportionate to gamma squared?
Yeah, instead say.
I think it will be proportionate, but it will happen more quickly. But
but regardless of how the formula looks like, wouldn't you have been able to get to sort of the same conclusion about the optimization anyway? It seems to me you're sort of fitting your theory backwards in this way. So you have a methodology problem.
I don't know if I see what you mean. If there is gamma square, to me it doesn't change many things. And
did you try to do your experiment at the same time, or for example with different shapes, or with this different shapes of the cubic you used, or not, and to control your experiment and to compare your results?
doing more than one experiment at the same time, it was a bit difficult. As I said, I hit the box and I measured the range thanks to the sheet of paper. Concerning the shape of the box, I used this shape and this kind of shape. And as I said, if I would have had more time, I would have been very interesting to study the influence of the shape.
My question concerns the method of hitting the box. Haven't you considered the possibility of hitting it by a pendulum? By a pendulum.
That's a great idea. I didn't think to this, and if I thought to this, maybe I would have used it, and it would be a way it would be an answer to the question. The question before, to hit the box like this and to quantify the energy. But in practical experiments, it would be a bit harder to make, but it would be very possible.
And the last question from jury member.
Could you please explain theoretically the optimal ratio with this 30% and the plot non-monotonic yes, here, range of ratio.
Theoretically, it's quite hard, but we can have a close look at the limit points. As I said, if the radius is closed, we have a closed box, and we don't have a good ring. And if the radius is open, we have a vortex cannon, but it does not propagate in an efficient way. So we should have a maximum, and this maximum is due to the discontinuity. And experimentally, I find this maximum. Now, to explain it in a theoretical way, I must admit I didn't find a theory on that. And if anyone of here have the theory, I would be pleased to know it.
Okay, thank you. Now that we decide the marks, we will start the grading with grading the reviewer, Ukrainian team. Nine, 7, 9, 9. We'll start once more. 9, 7, 9, 8, 9, 8, 10, 8, 9, 8, 9, 8, 8, 8, 8. Now grades for the opponent, the team of Denmark. Eight, 7, 8, 8, 8, 8, 7, 8, 8, 6, 9, 7, 10, 7, 7, 7, 8, 5, 8, 8, 8. And now for the reporter. 7, 7. We will start one. 7, 7, 9, 7, 7, 8, 8, 8, 8, 9, 8, 9, 7, 7, 8, 8, 8, 7, 7, 6, 7, 7, 7. Drew remarks or comments on the lowest, highest grades.
Apparently I have put the highest grades for the opponent and the reviewer. The reasoning is simple. I thought that the most important physical questions were mainly raised, discussed, and the discussion was productive, and I thought it's good to grade that, even though it wasn't ideal, let's put it like that. Thanks for that.
Okay, I wanted to make a little comment for all three teams. I really liked the play. Why the reporter has got only 8 from me? It's because maybe I didn't understood how did you use your theoretical results, for example, your theoretical analogies, and you didn't use it to produce some maybe estimated dependencies on the range of the parameters of the system. And you didn't calculate the Reynolds number, which is important, and one more issue is that you have said that your velocity or distance depends somehow linearly of the your distance depends somehow linearly on velocity. I didn't catch it really, but you didn't say by which formula do you take your drag force. You could just use some drag force for some aerodynamical object, and to estimate the range, what is the dependence on the distance. And what about the reviewer and opponent? The reviewer did his job perfectly, and he just showed that the opponent didn't do it such well. Because the questions raised by reviewer were practically perfect, and I think the opponent could raise it to many of them. Thank you.
I would like to explain why my marks were the lowest, systematically for reporter, opponent, and reviewer. As I told at the beginning, I was involved in IYPT for pre-university students for many years, and therefore I expected a little bit lower level for university students. Therefore, higher. Sure.
I very much was delighted with the experiments and the presentation, but I think you've missed one very important point which was raised by the reviewer, the difference between the self-propagation of the vortex and the wind which is just put out of your box. So it's why I haven't given you the highest marks, because your experiments were excellent. I also haven't understood the very nice analogy with Biot-Savart, what it had to do with the vortices. You haven't given any point how it helped your analysis. It was nice, but so and I found the reviewer very sharp in pointing the most important problem in the presentation.
As for me, the physics of the creation of the vortex in this box was not fully cleaned out, and I'd like to hardly believe that the only parameters that influence the range is the energy of the strike and the diameters. I would like to see some theory showing the physics of creation.
Thank you very much for the remarks.